Alice and Bob are playing a stone game where the stones are laid out in a row and each stone is worth some number of points. Taking turns, with Alice going first, each player grabs either 1, 2 or 3 stones from whatever is left at the front of the row, adding up the values of the stones they take as their score. Advanced level. The counter example that kills every greedy variant. Value sum, prefix sum, take the max of the next 3, all die on ouster to 377,377. Any heuristic that scores a move locally, instead of accounting for what it hands the opponent fails here, which tells you upfront this is a minimax problem, not an optimization over a single. Bounded branching factor of 3 from a fixed prefix is the whole reason this collapses to O(n). The state space is just the n possible suffixes, not a subset-based game. N up to 5, 10, 10 set 4 and negative values rule out anything exponential and confirm we need a closed form per index recurrence, not memoized minimax over game trees. This is the canonical zero-sum perfect information alternating move game, the same skeleton as stone game ICCC predict the winner. The trick that solves this one score differential DP is the trick that solves the whole family. The only thing that changes between variants is the move set and whether it's a prefix, a DQ or a general interval. 1000, 2000, 3, 6 total is 2. So a tie means both land exactly 6. Alice's only real branch point is take 3 versus take. One workout Y take 3, grab 1 plus 2 plus 3, 6 and Bob the lone 6 ties rather than loses. And you internalize why the recurrence has to subtract the opponent's best continuation rather than just maximize your own take. Skip the syntax tour. The one thing worth flagging is why float inface and not 0 as the initial best. With negative stone values, a real optimal gap can itself be negative. So seeding at 0 would silently clip valid negative gap answers. That's the kind of off by default bug that passes small tests and fails on adversarial input. Naive minimax with 2-track scores is O3n. The real inefficiency isn't the branching. It's that Alice's score, Bob's score, index has redundant state. 2 different score pairs at the same index with the same difference are interchangeable for every future decision. That redundancy is exactly what the next slide collapses. This is the standard reduction for zero-sum alternating games since final Alice final Bob is invariant to relabeling, state collapses from a pair to a scalar and the game becomes single agent. Every ply, you're maximizing your own gain minus whatever gap you concede to a symmetric opponent one level down. It is the same identity behind minimax state. Mnimax state, mnimax state, mnimax, state other player in general game trees, specialized to a linear array. dpig max over k in O1 to 3 of prefix sumi I plus k igp I plus k. Dependencies only point forward I on I plus 1 to ttp to t plus 3, so it's a DAG with no cycles. That's what licenses the strict right to left fill and rules out any left to right or two-pointed approach outright. The subtraction here isn't a penalty term, it's a roll swap. dpi plus 2 is that same player's best gap when there is the mover, so subtracting it correctly reframes it as a deficit. This is the part people get wrong when they try to hand roll variants, forgetting that dp always means gap for whoever moves here, not gap for Alice. O3 length time, On space, single pass, no recursion stack. This is already optimum for this move set. The inner loop bound at 3 is fixed by the problem. If the take set were 1.k for larger k, you trade this for a sliding window. Max trick to stay linear, which is exactly the harder variant in Stone Game 2. dp0 is a proof object, not just an answer. Is the guaranteed margin under optimal play from both sides. So the sign check is doing real work. No simulation needed to justify it. The recurrence already baked in both players playing perfectly. 15 lines. And notice what's absent. No explicit player state. No separate score tracking. No branch on whose turn it is. That absence is the signature of a correctly chosen state representation. If you find yourself adding a turn flag to a game DB, you've usually picked the wrong state. The index arithmetic to watch under pressure. Taking k stones from I covers I dot I plus quake 1. So the opponent's subarray starts at I plus quake, meaning you subtract dpi plus quake, not dpi plus quake 1. That fence post is the single most common bug when people implement this code in an interview. Worth checking dp1 112 by hand. From 2 to 37 the mover's best is taking all 3 dwell against an empty dp40. Then DP0 has to wait, take just the one, concede DP1 once swerves against take more upfront, against take more upfront, and every option loses by exactly 1, which is the sharp version of the greedy trap from slide 1, total stones sum to 13. And the best achievable split is 6 versus 7, not 1-2 versus 1. Before running it, does the negative value change the recurrence at all, or just the arithmetic? If your mental model says no change needed, you've correctly internalized that DP doesn't special case sign. That's the point of subtracting rather than branching on value. Here take 3 dominates unconditionally rather than by a margin of 1 like the previous trace. With a poison tail stone, the recurrence naturally prefers absorbing the whole prefix over leaving any residual for the opponent to be forced into. Same code path, no special casing, the sign just falls out of the sums. The subtler fourth mistake, word naming for an interview, initializing best to 0 instead of inf. It passes every positive value test case and silently breaks the moment a valid best is negative. A bug class you won't catch without a hostile test, which is exactly why interviewers plant negative values in this problem. MemoS top-down has identical asymptotics to the loop, so this isn't a complexity argument, it's a Python-specific one. Python 10sen4 deep recursion blows the default stack limit, and even with sys.sense set recursion limit raised, function call overhead makes it measurably slower in practice than the flat loop. Bottom up is the strictly dominant choice here, not just a style preference. The all negative case is the one worth stating, precisely. Optimal play there means minimizing your own loss, and the recurrence handles that identically to the maximizing case because it was never actually maximized score, it was always maximized score minus opponent's best response. A minimax framing is symmetric to sign by construction. The generalization worth having ready, any prefix-suffix decay alternating game, where the payoff is additive and zero sum, reduces to this same score differential DP. Stone Game 2 relaxes the fixed take, set to a growing window, still only via a different state. And predict the winner is this exact problem on a DQ instead of a fixed row. If you're asked to extend this to picking from either end, expect the state to grow from one index to an IE. Jake's TPO. Quick one. Piles are 1, 2, 3, 7. If Alice always grabs the biggest pile available, does that greedy play actually win? Pause and guess. Take a second. Think about what Greedy leaves behind for Bob to pick from. Greedy actually loses here, grabbing 7 first hands, Bob a juicier remaining split. That's exactly why the DP checks taking 1, 2 or 3 piles, not just the biggest. Second one, when there's only one pile left in the row, what's the DP value for that state, and why don't you need any look ahead to know it? Think about it. This is the base case the whole recursion bottoms out on. With one pile left, DP is just that pile's value. The player takes it, game over. Every other state in the table is built by comparing against cases like this one.